Thank you very much for that introduction. I am super excited to actually talk about something related to Ghost here, especially in New Orleans. So my name is Yuanzhi. I'm a PhD student from the City Design Lab, Purdue University. Today I'm going to present GhostAR, a time-space editor for embodied authoring of human-robot collaborative tasks with augmented reality. This work is in collaboration with Tianyi, Qian, Pawan, Manav, and Professor Karthik Ramani. So what is GhostAR? In a nutshell, GhostAR is an authoring system for human-robot collaboration tasks. The key feature of GhostAR is that it visualizes humans' physical demonstration with in-situ AR avatars, which we call it a ghost. And then using these ghosts as time-space reference, user can then program for collaborative robot behavior. So before we move into the details of GhostAR, I would like to talk a little bit about the background of robot programming or task planning. Okay. Through all these years, we have been figuring out a lot of different ways that allow users to intuitively program tasks for robots through graphical user interface, tangible user interface, and physical demonstration. However, for most of these methods for programming robot, after the robot is being programmed, they're most likely operating by themselves in isolation. That is not the case for human-robot collaboration. In human-robot collaboration, or HRC, humans and robots are two equally important parts during the operation. And therefore, if you want to plan a task for HRC application, you not only need to plan for the robot, you also need to plan for the human at the same time. And more importantly, since humans are actually working with the robot collaboratively and they are working towards a common goal, they're not working in isolation, right? And that means during the operation, they must be constantly adjusting and adapting to each other's uncertainty in order to work in a collaborative manner. For example, if I notice my partner is working at a higher speed than I am, I might want to consider picking up my own speed in order to keep up. Okay, so you see all of these little things needs to actually be taken into consideration when you are planning for HRC tasks. And that is why traditional method for robot programming cannot be successfully adopted for HRC application. So prior work on human-robot collaboration predominantly used this method to program a task involving using two humans demonstrating the task and with one of them actually acting as a robot. You see, this method automatically establishes the collaboration, the correspondence between the human and the robot through physical demonstration. And it's actually establishing, adopting a philosophy of programming by demonstration, enabling users to program robot behaviors with natural human motions. However, since this method does not have a digital interface, it supports very little sophisticated editing after the robot has been planned, and therefore resulting in relatively simple tasks. So inspired by the prior work as well as our own knowledge, we decided to adopt an augmented reality interface on top of programming by demonstration method to create our own system. So the workflow of GhostAR can be illustrated in these pictures. To program a human-robot collaborative task, the user first demonstrate the human's action by physically demonstrating the human part of the collaboration, and then his motion is captured and recorded and displayed as a series of human ghosts. Using these human ghosts as time-space reference, the user can then program for the collaborative robot behavior. At this point, the task planning for the HRC has already been finished, and then the user can proceed to actually carry out the collaboration with the physical robot by simply repeating what he has done before, and our system is capturing his real-time motion, compared to his authoring content, and then find out the corresponding robot behavior, then issues the command to drive the physical robot, then completing the human-robot collaboration. So essentially, this is how GhostAR works. And then our system actually supports two types of human-robot collaboration, including synchronized and trigger. For synchronized collaboration, the human and the robot action takes place at the same pace, while for the trigger action, the robot action is actually triggered and takes place after the human action. It is important to mention that our task adopts the type of human-robot collaboration as human lead, robot assist, meaning that the action is always initiated by the human user while the robot always tries to adapt and assist the human user. There are a few different types of human-robot collaboration which are not the focus of this work. So now let me actually describe and explain the actual system design of GhostAR using an example. This is the example. The example involves one human simultaneously collaborating with two robots. And the human, in the example, delivers the object onto the table, and the arm bot then picks it up and puts it into the basket. Meanwhile, the camera bot follows the human and videotapes the entire process. Okay. So in order to complete this human-robot collaboration using GhostAR system, the user first physically plays out the human part of the human-robot collaboration by acting it out, and then our system captures his motion and represents it with an animating AR ghost. And using these AR ghosts as a time-space reference, the user can then define the part of the human motion he wants the robot to be collaborating with using the grouping function, and then assign robot collaboration choosing from synchronize or trigger. To program a synchronized robot collaboration, the user can simply just manipulate a virtual robot while having the human ghost as the time-space reference, and therefore simultaneously establishing the correspondence between the human and the robot. So in this case, if the human moves faster, the robot will move faster in order to keep up. In terms of the trigger human-robot collaboration, the robot is literally triggered after the human action. In our case, this robot arm will start picking up the object after the human put the object onto the table. Okay, so when the user finished the authoring, he had the option to actually go into the preview mode and preview the entire task using AR simulation to make sure that everything is working as intended before he moved into the action mode and actually carry out the collaboration with the physical robot. When he simply needs to repeat what he has done before, and our system makes it easier for user by providing a guiding AR ghost and then completing the human-robot collaboration. So essentially what is happening during the action mode when the user is carrying out the collaboration with a physical robot is that there is an underlying collaboration model in our system that takes in the human's real-time motion as input and compared with what he has authored based on the authoring a human ghost using the motion mapping algorithm based on dynamic time working. And then based on this result, we'll be able to find out the collaborative robot behavior, then issue that to drive the physical robot, and then completing the human-robot collaboration. So it is worth mentioning that our system is based on our motion mapping algorithm is based on dynamic time warping. So essentially what it does is that it finds out the similarity between two time series. And in our case, the first time series is when the user is authoring the human part of the motion, and then the second time series is when he's actually acting out during the action mode. So our system, the entire AR authoring system is developed using Unity engine. And you also notice that during the, if you want to author a robot behavior, you actually manipulate through a virtual robot. So in order to provide realistic robot simulation that best mimic the real dynamics and physics of the physical robot, we adopt ROS as the backend robot simulation engine. Here we demonstrate a few more examples using GhostAR system, including human-robot joint assembly task, light providing flying drone in a dark room, and also a handshake example with a tower bot. To evaluate our system, we have conducted a 3-session user study and invited 12 users. And the first session of the user study is to evaluate the motion mapping algorithm with our system, where we ask the users to perform a series of human motions. And according to this result, we can see that our system is capable of achieving fairly high synchronized action progress estimation results. And in terms of trigger task detection, according to our result, the difference between the system detection time and the ground truth can be achieved within 300 milliseconds, which is pretty good. So the second session of the user study is to evaluate the robot authoring interactivity, where we ask the users to manipulate a flying drone as well as a ground robot to try to follow a pre-programmed human ghost as close as possible, while trying to then calculate the distance arrow as a result. Okay, so as you can see that from this figure, the drone is a little bit harder to manipulate than the ground robot, obviously due to the added degree of freedom. But more interestingly, we can see that an experienced user which has been practicing this task for 5 times is capable of achieving much, much higher accuracy than an novice user, indicating our system is pretty easy to use and master. The third session of the user study is to evaluate the overall usability of our system, where we ask the users to perform a comprehensive drawing assembly task with a gripper bot. And according to the user feedback, we find out that users generally enjoy using our system, and they get relatively high ratings for the user experience ratings. Especially in terms of the ghost. They particularly like the ghost, using the ghost idea to simulate and visualize the robot authoring before anything physical takes place. Okay, so the user does like the ghost. However, we find something interesting in the conflict. Like some users mentioned that the ghost can actually be obtrusive or destructive at some time. So whenever there's too many ghosts in front of their face, they feel like they can't see whatever they actually wanted to see. So this actually brings out a very, very interesting question, probably an important research question for future endeavor, is that how can we balance between clear authoring view and instructional AR content while providing both to the user? Well, I believe that the answer to this question might open potential new directions for future endeavors. So if there's one thing I would like you to take away from my presentation, is that GhostAR is essentially an authoring system for human-robot collaborative tasks through embodied demonstration with AR Ghost as contextual time-space reference. Thank you very much for your attention. I will now be ready for any questions.
All right. Questions for the speaker? Maybe while we get the next person to go set up as well. All right. So I've got one to start us off. So this seems to work really well for sequential tasks. So you had the example where somebody has to bring an object over, place it, and the robot picks it up and does something with it. Is there anything that comes up as a challenge, or maybe how do you handle the case where I need to be working with the robot back and forth, so maybe it needs to carry something with me to a goal, and then I need to place it, and then it takes it from there. So that back and forth seems to add complexity, because the simulation in the prototyping stage is going to not actually have that physical assistance, right?
Well, in that case, actually we have concluded that most of the complex behavior back and forth between human and robot can actually be dissected into the unit synchronized or trigger task. And most of the local robot behavior is actually handled by the robot itself, such as detecting the obstacles and automatically do some simple decision makings. But yeah, in terms of the to answer your questions, we think most of the questions can be dissected into a trigger task and synchronized task.
Okay, great. Other questions? All right, let's thank our